So if you have something like x squared y over x to the third y to the fourth, I hope that everyone would know that there's two x's on the top, three x's on the bottom. So all two of those cancel with two out of the three of those. So I have an x on the bottom. And that y cancels with one of those y's. So I have three y's in the bottom. We can do that, right? That's laws of exponents. Dimensional analysis is the same way. So dimensional analysis, you probably heard the name and you're probably like, I don't know what you're talking about. So do you guys know the metric system? Yeah. Okay. Before you guys graduate high school, please, especially if you're going into a science, math, or STEM field, before you graduate high school, know at the very minimum the basics of the metric system. Kilo, hecto, deca, base, deci, centi, milli. At the very minimum. Because you're going to be in a university filled with other science majors, math majors, and engineering majors, and I guarantee you they will know the metric system like no one's business, especially if they're coming from like another country, because that's what they mainly use all the time, 100%, all the time. Cool? Okay, so there is our background knowledge that we need. And of course, you know, all these formulas can be derived, guys. So anytime you hear the word angular velocity, that just means how fast something is rotating. Keyword rotating. Cool or not cool? So if you hear someone say you're doing 3 revolutions per second, that's angular velocity. If you hear someone say you do 90 degrees per second, that's angular velocity. If you hear someone say you're going pi over 2 radians per second, all that is angular velocity. Anything that has to do with rotation is angular velocity. Now, what is linear velocity? Linear velocity is distance divided by time. That's it. And notice, we're not even bringing up formulas. Yes, you can use all these. This is usually angular velocity, but as long as you got the correct units, you don't need to tell me symbols. So, and if you go to the next page, guys. They give you more formulas, and they're like, oh, algebraically, your omega is your theta divided by time. Yeah, because that's how much you rotate divided by time. And your linear velocity is a divided by time, where a is distance traveled. Because they told you over here, oh, look, there's the distance traveled. That's an arc length. And then they told you down here, oh, look, your arc length is, yes, r times theta. Guys, these formulas come from somewhere. Look, I'm not even going to mention, well, I guess we're mentioning formulas right now. But look, where did arc length? Oh.
Mr. Calvin?
Yes, ma'am.
Can you send Lauren to the counselor's office, please?
Yes, ma'am. So where did arc length come from? Well, remember we said arc length was just a percentage of circumference? Do you guys remember that? So here's your percentage. Theta over 2 pi, because 2 pi is a whole revolution. And what is circumference? 2 pi r. OMG, look at that. 2 pi's cancel out, and you just get theta r, which you already know. Look, there it is, r theta. That's arc length. Okay, if you got nothing out of that, all you got to do is that you can derive everything from scratch. You don't need any formulas. And that's the whole shebang. All right, do you guys have a calculator with you? Okay, let's get a calculator. Get a calculator with you. Yes, but we're probably not going to be using it anyway, so like we're not going to use sine, cosine, at least not yet. Okay, here we go. We're going to go slow, guys. We're going to go real slow. And I'm not even going to mention formulas. Now, there was one student yesterday that said, just give me the formulas. And then after class, I met with her and like, look, here's the formula, just use this. And she liked that better. I personally don't want you to go that route, but if you want to go that route, just bother me at the end of class and say, Chavez, just give me formulas. And we'll give you the formulas and you can go that route. But let's see if we can go this route. Cool? All right, so here we go. An LP long play record, do you guys know what that is? It's like where the vinyl records go. Okay. Is in the figure to the right. It rotates at 33 1/3 revolutions per minute. So before I even start, is that right there that they give us angular velocity or linear velocity? Angular, because it deals with rotation. So that's angular velocity. You can use the omega symbol if you want. It's understood that that means angular. All right, letter A. Find the angular velocity in radians per second. If it did not have this radians per second, if it just says find the angular velocity, I would just type 33 1/3 revolutions per minute. But because it tells me specifics, what units do they want? So I'm going to transfer it. I'm going to translate this into radians per second. So first and foremost, do you guys like fractions or mixed fractions or decimals? Fractions? Both? Okay, it doesn't matter. Is it okay if everyone knows that 1/3 is 0.333, right? Okay, so is it okay if I do this 33.33333 just to make it? Okay, so I'm going to write 33.333 and I'm going to put revolutions like this, and I'm going to make a T-chart. Do you guys remember T-charts? From like chemistry maybe? And on the bottom I'm going to put minute. So the whole point of a T-chart is that I want to cancel units. So what do I want to cancel? Well, I want to cancel rev because I want radians. So I'm going to write down here, in one revolution, how many radians do you have? Yeah, I heard someone say it. What is it? 2 pi. So write 2 pi and then put RAD, rad, for radians. So there it is. The revolutions cancel. At the moment, I have radians per minute. I don't want radians per minute. I want radians per what? Seconds. So in 1 minute, how many seconds do I have? So there it is. Whatever I have in the top, I'm going to multiply. Whatever I have in the bottom, I'm going to multiply, and then top divided by bottom. That makes sense? Look, don't worry. All I'm saying is this. 33.333 times 2 pi. Whatever answer you get, you're going to divide by 60. So I take, that is so what?
We're good. We can move on.
No, yeah, once you're super beast, you no longer have to do all this stuff. You know what? I'm gonna do this. Do you know there's a hack? I feel like TikTok. Oh, they don't know this, but let me tell you. So here's the hack. Push alpha y equals, and you see number 2 where it says UND. That's a mixed fraction, and you can type in there 33 and 1/3 like that. Times 2 pi. I'm going to push enter, and whatever that is, I'm going to divide it by what? 60. 3.490658. Yes. Alpha y equals the number 2. 3.490658. Radians per second. Yeah.
You want the whole thing, Tom?
You can leave it in terms of pi, I guess. Multiply 33 1/3 times 2 divided by 60 and leave it in terms of pi. Yeah, the more digits, the better. I guess if the pi's not in the final answer, then it's rounded. Okay. Are we okay so far, guys? All right. So I'm going to do something that I did with, I did an experiment yesterday. I tried it with, I think, first period, and then I did something different with fifth, and then I feel like I should have just done everything the way I did it the first time around. All right. So letter B. Are you guys ready? It says, oh, you don't like the T-chart? Okay, so let's talk about the T-chart real quick. So, side note. Don't worry, yeah, because a lot of you maybe haven't done T-charts and stuff like that. You don't have to use the T-chart once you get really advanced. I'm just using a T-chart just right now so you can do dimensional analysis. So you don't have to use it. So if I told you I want to know how many seconds there are in a year. So here's what you do to you if I wanted to use the T-chart. 1 year, and I go like this with a little t, and then I want to cancel years, right? And I go in 1 year, there's how many months? 12. Actually, let's just go right to days. How many days? So I'm going to write 365 days. And then I want to cancel days, so I'm going to write in 1 day, how many hours? 24. 24 hours. And then I'm going to write in 1 hour, how many minutes? 60 minutes. And then in 1 minute, how many seconds? And this is how you use the T-chart. Minutes cancel out, hours cancel out, days cancel out, year cancel out, and you're just left with seconds. So how do you use it? 1 times 365 times 24 times 60, and that will tell you how many seconds there are in a year. You've never used? Yeah. Okay, so you see how all the units cancel out and you just have seconds? So now you just multiply the whole top row. 1 times 365 times 24 times 60 times 60.
Oh, so like what we did here.
Yes. But I was just trying to explain how to use the T-chart for for something long like that. You know what I mean? Now, don't be doing this once you get to grad school. Once you get to grad school, by then, I expect you to be pretty good with the dimensional analysis. But right now that we're rookies, use your T-chart. What's up? Yes, whatever you get in the top, the product of the top divided by the product of the bottom. So if you have A, B, and C here, you multiply these three together, and it's the product of the top divided by the product of the bottom. That makes sense? Okay. All right, I think we're good now. All right, so here we go with this one. We're going to do this two different ways. I'm going to show you guys one way that I think will make sense to you, and I'm going to show you guys a hack. And I'm going to make a TikTok account, and like, oh, they don't know this, but my first TikTok is going to be things students say. That's, yeah. I already have the first line of the. Sir, is this going to be on the test, sir? Okay, I'll stop. You guys don't say it, but others do. Of course. All right. Here we go. Sorry, guys, that I got you guys sidetracked. Find the angular and linear velocities of the record per second at the point at which the needle is located when it is just starting to play 14.5 centimeters from the center. So if I look at this record player, they're talking about the linear velocity here. And of course, the angular velocity, they want it as well. The angular velocity is the same. It's this. No matter where you're at, you're rotating at that speed. Does that make sense to you guys? So the angular velocity is the same. And in a little bit, we'll write it. I care more about the linear velocity. So how fast is this record player going? So what they're trying to tell me is, imagine that record player being a tire. If this were a tire, how fast is it going? If this were like a tire in a golf cart, and you looked at the odometer, how fast is, or the speedometer, how fast is it going? So let's find out. Yeah, it deals with this right here, with this, right? Yeah, so check it out. Don't write this down, just listen. So do you agree that this tells me that I'm going 33 1/3 revolutions per minute? All right, and in one revolution, do you agree that I cover the entire circumference? And circumference of a circle is 2 pi r, no? All right, so I'm going to go 2 times pi times 14.5 centimeters, and this is how much distance or ground it covers every time it does one revolution. Cool? All right, so I'm going to take my calculator. Don't write this down, just listen right now for now. 2 times pi times, what did you say, 14.5? And I get this number, 91.106. So I'm just going to put that for now, 91.106. And this is centimeters for one revolution, right? So I'm going 33 1/3 revolutions per minute. So I want to find out what my speed is in centimeters per second. Why? Because I'm going to do a hack in a little bit, because this is in seconds. So check it out. I'm going to go 33 1/3 rev per minute. Don't write this down, just listen. And in one rev, I cover 91.106 centimeters. And that cancels my rev. Now I need to turn that minute to seconds. In 1 minute, there is 60 seconds, correct? All right, so let's see. Let's see all this work. Yeah, don't write this down, just listen, because in a little bit I'm going to show you a hack. And hopefully you'll like the hack. 33 1/3, I'm just doing this right here. 1/3 times, what did I say? Times 2 pi 14.5, so this number up here. And then whatever that is divided by what? 60. Enter. So this is my speed. 50.6145. 50.6145 centimeters per second. Which is fine. You can do, did all that make sense? Okay. If you already have this answer, okay, don't write this down, guys. Don't worry, because I want to show you this hack. If you already have this answer right here, you see this answer, the 3.49? You can go right to the speed immediately. Let me show you how. Let's look at this hack. You just go 3.490658 radians per second, and then you're going to say this. In 1 radian literally means radius. What is your radius of this deal? So I bet you if I take this 3.49 and I multiply by 14.5, it's going to give me that number. I bet you it is. If not, I'm fake. Let's see. So where is it? 3.49. Here it is. That one times what did we say? 14.5. And let's see. 14.5. Enter. Look at that. Digit per digit. It's the same. Do you guys see what's up? So isn't it a lot faster to do the hack to just take this radians per second and just multiply it by your radius? All right. So write down whatever you think is important, guys. I'll put all this work there for you guys. That's a second, yeah. Notice how we haven't brought a single formula in. If you're wondering, Chavez, why are they the same? Because if you think about it, that 91.106 is 2 pi times your r. Do you know what I mean? So that's why the one in blue works. You can just all it's missing is your r, because you just 2 pi is 1 revolution.
Oh yeah, it's seconds anyway. But if this wasn't in seconds, you have to do it.
Well, because they didn't tell you the units, you could have left it in minutes and you would have been correct. You know what I mean? It's centimeters per second at the moment. You could have left, but you could have left it as centimeters per minute because it doesn't specify. Linear velocity is distance divided by time. So miles per hour, kilometers per hour, meters per second, anything like that. Does that make sense, guys? All right, here we go. The most important question from question 1, or from example 1. Find the angular and linear velocities per second at the center of the turntable. Okay, the angular velocity, it doesn't matter where you are at on this turntable or on this vinyl player, the angular velocity, anywhere you're at, you're still spinning at the same rotationary speed. Does that make sense? Yeah. So the angular velocity is still the same. 3.490658 radians per second. No matter where you're at. But let's talk about the linear velocity. How much distance you cover. So pretend you're a bug. You're a little bug. What's your favorite bug? Like a cockroach or something? Guys, I did that on purpose. I apologize. All right, pretend you're a ladybug. So here you are, you're a ladybug, and you're right in the center of this vinyl. We want to know how much distance you've covered. If you're at the center, all you're doing, if you're a ladybug, you're just going. That's actually kind of fun. All right. All you're doing is spinning. Have you traveled any distance? No. So what is the linear velocity at the center? 0. Make sure to put units. 0 centimeters per second or minute or whatever. I used to have a kid. He was a valedictorian of the class of, I think he was 2013 or from Southside. And his name's David Cruz. And he would always write 0, and then he would put an outrageous, like a crazy unit, like miles per miles per hour, miles per, like, yeah, because no matter what, like, he's correct. You know, it's still, so, yeah, he's a smart little kid. Well, he's an actuary now, so he does actuary. This is his 3rd year at USAA. So he does like math, like analysis, risk analysis and all that. He's a good kid. He's doing well. All right, let's go to the next page. Does everyone know what a bike is? No, you think it's funny, but in about another 30, 40 years, we're going to have kids that have never ridden bikes. They're going to be in hoverboards and electric machines, you know, So here we go. Yeah, everyone, if you've never had the experience of riding a bike, go ride a bike, guys. It's fun. This in the front is called a front sprocket. This in the back is called the back sprocket, and then there's a wheel attached to it. So we got to know a few basics, just a little bit, a few basics. All right, guys, focus. Does everyone agree that if the back sprocket does 1 revolution, that the back wheel also does 1 revolution?
Yeah.
Okay. Does everyone agree that whatever the speed, the linear speed of the front sprocket is, it's the same as the back sprocket, the linear speed, because it's connected by a what? Chain. So make sure that we understand a few things. So what do we understand? The back sprocket, because it's connected with an axle to the back wheel, every time it does 1 revolution, the big wheel does 1 revolution. Now, what's the connection between the back and the front? It's linked with a chain. So every time that whatever the linear speed is of that, it has to be the same for the back, or else the chain is falling off. That makes sense? What's up?
But they're different sizes.
The linear speed's the same, but not the angular speed. Every time this rotates 1 time, that little one rotates a whole bunch of times.
Oh, yeah.
Yeah, okay. So don't get intimidated on the exam. You're going to have a question like this, and it's going to have a whole bunch of sections. Don't get intimidated. Do it 1 question at a time. It's really simple. You just got to go slow. And I'll show you how to not be a robot, how else you can do it a different way. All right, let's go. Example 2. It says, a cyclist turns the pedals of her bicycle at 8 radians per second. So underline that. It's probably going to be important. The front sprocket has a diameter of 20 centimeters. So that means the radius is what? 10. So I care more about the radius than the diameter. So 10 centimeters. Travis, why? Because 1 radian is whatever the radius is. And it's connected by the chain to the back sprocket, which has a diameter of 6. So that means the radius is 3. So I'm going to zoom in, and I'm going to put that is 3. Let's see, what else does it tell me? Which the rear wheel has a radius of 35 centimeters. Okay, so here's my rear wheel. That has 35 centimeters. So there is my diagram with all my labels. That's a 35. Sorry if it came out kind of. All right, what else? And it's connected to the back sprocket, yeah. All right, let's go slow. What is the angular velocity of the front sprocket? Okay, well, how fast am I pedaling? So if I pedal at 8 radians per second, and because this is attached to my front sprocket, doesn't that mean that my front sprocket has to be going the same angular speed? Yeah, so 8 radians per second. And if you need a description, put that the pedals are attached to the front sprocket. Are we okay so far? What's up? Yes. Yeah, she's hitting up the pedals, and the pedals are attached to the front sprocket, so yes. Every time the pedals do 1 revolution, the front sprocket does 1 revolution. All right. Yeah, ask yourself that, guys. Whenever you get tired and you're like, what? I don't understand. If the pedals does 1 revolution, does the front sprocket do 1 revolution? Yes, perfect. So it has to be the same, 8 radians per second. Letter B, what is the linear velocity of points on the chain? So they want to know how fast that chain is going. So here's how you're going to do it. You take your angular velocity, 8 radians per second, and you do your hack. In 1 radian, what is my radius for the front sprocket? 10 centimeters. The radians cancel out. What is 8 times 10? So 80 centimeters per second is your linear velocity of the chain. Does that make sense to you guys? Okay. So now we know how fast the chain is moving. So letter C. What is the linear velocity of points on the rim of the back sprocket? So let me look at the back sprocket. If you're on the rim of the back sprocket, you're looking at these blue dots. Aren't those blue dots touching the chain? And how fast is the chain moving? So that 80 centimeters per second, right? The chain is moving. The linear velocity of the chain, right? So that must mean that this has to be moving 80 centimeters per second. Because it's connected by the chain. If it's not moving at 80 centimeters per second, then the chain is falling down.
So, okay.
Do you know what I mean?
Yes.
Does anyone have any questions? Please ask. What's up, Gonzalez? Yes, it's connected by the chain, And since I want to know the linear velocity of the back sprocket, it has to be the same. Yes, well, it could also be a belt or something, but we'll get to that when we, like in the next session. All right, here we go. So here's your question, Ms. Abdul Karim. What is the angular velocity of the center of the back sprocket? Guys, it is obvious that the back sprocket is spinning faster because it's little. Every time the big one does one revolution, that little one does a whole bunch. Cool or not cool? So here's how you can do it. Here's what high school Chavez would do if I were a little kid. Because I'm trying to go as fast as I can. I'm not, well, I am calling you guys little, but it's because you guys are little. Okay, so here we go. The way I would do it, guys, I would take this linear velocity and I would convert that into angular velocity for the back wheel. So I would have gone 80 centimeters per second. And then for the back wheel, how many centimeters are in a radian? Remember, that means radius. No, not I did say back wheel, sorry. For the back sprocket. 3. So for the back sprocket, I would go 3 centimeters, 1 radian. And this will tell me my angular velocity. So let's see, 80 divided by 3. I take my calculator, 80 divided by 3. Don't worry, I'm going to tell you a hack in a little bit. 26.666667. 26.66667 radians per second. Cool or not cool? All right, so check it out. I'm gonna show you a different way. If I were a high school kid and I was not in a hurry, and I just had time to just think about it for a little bit, here's what I would do if I were not in a hurry. I'm looking at this big circle, I'm looking at that little circle, and I can see that they're linked with a chain, and I know, like, okay, all I need is a scale factor to figure out how much more the little one is spinning. So I know that my big R is 10. When I say big R, the radius of the big one. And I know that my little r is 3. That ratio, 10 divided by 3, you could also do 20 divided by 6. 10 divided by 3. So what this ratio tells me is that every time the big one does 1 revolution, the little one does how many? Perfect. So this is my scale factor. So don't I already have a speed in radians per second for the front sprocket? Wasn't it 8? So if I take this number and I multiply it by that scale factor, shouldn't I get the same exact thing? No, you just do the 8. You said pi. Just the 8 radians per second and multiply it by that scale factor. And it's going to be the same. If it's not, I'm a fake. And I don't want to be a fraud. So let's see. That times 8. And let's see if we get the same thing. Look at that, guys. Did we get the same answer? If you sit down and just calm down for a little bit and think about it, you will get it right. Notice, have we brought any formulas in? No, we've just done everything just with logic. What's up? What's up? Oh, the radius of the front sprocket. So let me put it here for good notes. You can also get scale factor, which happens to be 3 point what? I already forgot it. 33333. And then go 8 times 3.333. I put that for good notes for you guys. Is this making sense to you guys? Be honest. Okay. Yes, ma'am. You guys ready for the next one, guys? All right, here comes the most important question. Yes, what's up? Yes, I got that from the scale factor, 10 divided by 3. All right, the last question, which is the most important one, we want to know how fast this bike is going. Because that's the whole point. Like, the whole point of this is to know how fast something is going. So when you're a awesome engineer for NASA, They're going to ask you, how fast is this meteor coming at us at? Okay, well, let's find out. Do I know, let's see, what's the connection? Do I know the angular velocity of the back sprocket? Didn't we just calculate that? Yeah. Why am I asking that? Do you agree, I'm saying angular, do you agree that the angular velocity of the back sprocket is the same as the wheel? Yes, every time the back sprocket does one revolution, the big wheel does one revolution. So I'm going to take this, the angular velocity, and I'm going to convert it to kilometers per hour. So Chavez, how do you do that? Well, first do baby steps. I'm going to write 26.6667 radians per second. What's up? Oh, yeah, you can do that. 26 and 2/3. And in 1 radian, what is the radius of the back wheel? Perfect. 35 centimeters. So now radians cancel out, and I have centimeters per second. Is that what I want? Well, yeah. It's not what I want linear velocity, but I want it in kilometers per hour. So here comes my metric system stuff that hopefully we know. And I'm like, okay, how many centimeters in a kilometer? Do we know? 100,000. All right. Yeah, okay, let me show you how to do that, guys, because that is important enough that we got to talk about it. Side note, for the side note, before you graduate, make sure that you know these acronyms: kilo, hecto, deca, base, deci, centimilli. Cool. I think there's like King Henry died, merrily down central. I don't know. I don't remember. But make sure you know at least those. There's others. There's micro, there's pico, there's giga. But make sure you know those, because those are, they come out all the time. Are we okay? All right. So here's how you do it. You got to know which one's bigger. So the ones on the left are bigger than the ones on the right. Do we agree? And here's what you do. If you're on centi and you want to know how to go from centi to kilo or kilo to centi, it doesn't matter. You're going to count how many zeros I have to add. So let's see. I'm at centi and I want to go to kilo. 1, 2, 3, 4, 5. So I'm going to add 5 zeros. Put a 1 and then 1, 2, 3, 4, 5. And then centimeters.
Wait, what the heck?
Do you see how I did it or no? Yeah, and that's the beauty of the metric system, that you can go by 10 every time. So that's why the metric system is so beautiful. All right. So there it is. Right now, I have kilometers per second. Is that what I want? No. Perfect. So demerit, because you're yawning. I'm kidding, miss. That was a joke, but it's not funny.
Is that a straight up a demerit? Like, I can't demerit.
Miss, it was a joke. Come on, guys. 3,600 seconds in 1 hour. Yes, you can do it 1 hour, 60 minutes, 60 minutes, 60 seconds. But what's 60 times 60? 3,600. There it is. So just 1 hour, 3,600 seconds.
How do you know it's put on the top of the bottom? Is that just kind of like...
No, whatever you want to cancel. What do I want to cancel? I want to cancel the seconds, right? So I put seconds on the top because I want to have hours in the bottom. Look, kilometers per hour. That's all you have left. So Chavez, how do you do this? Because I don't know how to. Whatever you have on the top, you multiply. Whatever you have in the bottom, I guess you could also group and multiply. But there's only one thing in the bottom. So here we go. I take my calculator, and I go 26 and 2/3, you guys told me. So alpha y equals number 2, 26 and 1/3 or 2/3? Or none of those? Yeah, 2/3. Sorry. Times, and I already forgot, short-term memory, 35 and 3,600. Times 35 times 3,600. And then I like to push enter and then divide by 100,000. 1, 2, 3, 4, 5. 33.6. Kilometers per hour.
Bro, this bike is going pretty slow.
No, it's a pretty good speed. It's about, we looked it up yesterday. It's about 20 miles per hour. Now, I will warn you guys, last year, Okay, I do enjoy a comedy. Do you guys enjoy comedy? So last year when I was grading, it was a bike question, and someone told me that the speed of this bike was something like 3 billion miles per second. And they made me laugh, and I gave her a point. I didn't give her full credit. If you can make me laugh, I'll give you a point. So if you notice on the exam, it's all wrong, but you see +1, that means that I chuckled or I laughed or something. So guys, make sure it's realistic. A bike cannot go 3 billion miles per second, but this value is realistic. So make sure you always ask yourself, is this valid? Is that cool? How do you feel? Do we feel like we learned?
Yes.
Okay, so we're done. Let me pass out your activity. I do want it today, guys. I think we have enough time if you work together.